My name is Wade Henning, and I'm from University of Maryland, working at Goddard Space Flight Center. And on my team are Terry Herford and Avi Mondell, also of Goddard Space Flight Center, and Soko Matsumura of the University of Dundee. And also we recently just brought on board a graduate student, Joe Renaud of George Mason University, and he's been doing some absolutely fantastic work for the team overall. Now, what our team is involved in overall is a range of geophysical questions for rocky and icy terrestrial-sized exoplanets. And in particular, we tend to look at problems involving cases where tidal heating is so intense that it actually begins to alter the interior structure of a planet. For example, melting a pre-existing ice layer and turning it into a water ocean, or melting a previously cool and brittle silicate layer and turning it into a silicate partial melt layer, or even into a magma ocean in some circumstances. So we look at this from a variety of perspectives. The first of which I'll talk about here is the question of orbital circularization. So tidal heating causes orbits to circularize in general. The more intense the tidal heating, the faster an orbit will go through circularization. Now, we expected when we began the project that melting of a planet would be particularly bad for a small Earth-like planet in something like an early solar system where orbital scattering is common. And the reason for that is that if you imagine melting beginning in a planet, you're generally going to be decreasing the bulk viscosity of that planet. You decrease the viscosity, you decrease the amount of friction, you decrease the amount of energy dissipation, and therefore you decrease the rate of orbital circularization. Now, this would be bad if you are a young Earth in a situation where scattering in the solar system is common, and say you've been scattered up into a high eccentricity orbit. Oops. And having a high eccentricity for a long duration basically means you are left vulnerable to orbit crossings, possible ejections from the solar system, or even possible merger with the host star. So in general, we expected this to be a bad situation for young Earths. It turns out, however, that we've discovered the exact opposite phenomena occurs. So instead of melting decreasing dissipation of planet, it actually increases it by quite a lot. In fact, by a factor of at least 100 or more in most circumstances. So what happens is the opposite effect on the orbit. If you have greater dissipation, that means an orbit will circularize much faster. And this is great news for young Earths because it helps get you out of the way of crossing orbits with other planets on a much more rapid time scale. So we're trying to simulate this effect in general. Just to quantify it a little bit here, the curves on the bottom of this chart generally shows tidal heating, and unfortunately the scale seems to be a victim of lost in translation here. But the cases on the bottom here are cool planets analogous to our modern Earth. They have the least tidal dissipation of the cases we model. As you warm up, you go to these curves called warm Earth, and as you begin to develop a magma ocean, you only drop down a little bit to these central hot Earth cases. So what this means is that the coolest planets are the ones that have the least dissipation and therefore the least amount of orbital circularization. So orbital circulation is just the inverse of the amount of heating. So again, the effect seems to be good news for, quote, saving Earths from orbital chaos. I also wanted to talk a little bit about issues of habitability, because this group sort of has a mandate to discuss habitability in a general sense. My group generally does not talk about habitability too much, because we're usually talking about planets that have magma oceans, super hot planets. So not too much to do with habitability. But there are some circumstances where the two analyses overlap. And if you imagine a habitable zone at a typical G-class star up here at 1 AU, it's quite a ways from the range where tidal effects from a stellar tide tend to cause any alterations for the planet. But as you get dimmer and dimmer towards an M-dwarf star, eventually the habitable zone does begin to overlap with the stellar tidal zone. And the two can begin to have some effect on each other. Now, I should advise that in the next two slides, the comments I'm going to make have nothing to do with exomoons. which are a completely different story and different effects occur. So what I'm going to talk about has to do only with tides for planets orbiting a luminous primary and what it does to the habitability. But there's sort of a general expectation among folks that I've talked to that tidal heating and habitability tends to be equally good and bad. So there's a certain number of planets that are too cool to begin with, and tidal heating warms them up and makes them just right. And there's a certain number of planets that are just right already, and tidal heating warms them up further and wrecks them. Well, it turns out that that's actually absolutely not the case of what happens. Tidal heating for planets around luminous primaries is overwhelmingly detrimental. It's generally quite bad news, and for a simple reason. So if you imagine an Earth-like planet here with a habitable zone, inner edge and outer edge, where it has, say, 0 eccentricity and no tides, and compare it to a case where you increment up the eccentricity by some amount. Or you can change any other parameter that alters the tide, such as the internal viscosity or something like that. Tides actually scale as 1 over the, roughly 1 over the 6th power of semi-major axis. So distance from the star matters enormously. So what happens is if you increment up the eccentricity, the inner edge of the habitable zone moves a lot more than the outer edge moves. In fact, in many circumstances, the outer edge barely moves at all, and the inner edge does all the moving. So what you end up doing is you are cutting habitable zone widths by quite a substantial amount. So this is an example around a typical M-dwarf, and what it shows is a habitable zone width being cut almost in half by this effect. And it happens rather rapidly with a relatively small increase in eccentricity. Your habitable zones get cut almost in half, and it happens over a range of planet masses for which it's occurring. Now, I actually, when I went to check this, I wondered whether the habitable zone widths would be driven to near 0. So that does not happen. So there is sort of a silver lining to this. It's not completely bad news. The habitable zones are not completely wrecked, but they're not expanded either. There are a couple other fun issues that occur with this effect. Tides can also split habitable zones into a spectrum according to the planet mass, because tides couple better into larger planets. So a super-Earth and an Earth habitable zone may split in space. And in addition, you may have preferential reduction, where a super-Earth may have its habitable zone width reduced, but a 1 ME planet sees its habitable zone remain at the same size. And just to quickly mention issues with exomoons, everything that I just said about tides being detrimental to habitability do not apply to exomoons. In a sense, tidal heating is almost universally good news for exomoons. If you imagine a Europa or Enceladus analog, a small amount of heat goes a long way. Tides really matter most in cold environments, where the sun is weak. Just adding a little bit of heat to a planet can make a big difference for habitability, especially in the subsurface. Now, what this chart is actually showing is habitable zones generated for moons of various cases, where I'm not even talking about subsurface liquid water being generated. I'm talking about surface liquid water being generated in the absence of any insolation. And it turns out it's actually quite easy to do if you have large enough moons around large enough primaries. And if you're talking about super Jupiters, it's actually even easier to do for relatively reasonable eccentricities that might be out there. The only problem, however, is we don't really have statistics on exomoons yet. So saying anything really meaningful about this kind of has to wait until we have real data on exomoon masses and such. I just wanted to end with a couple points about other small topics that we're covering. One of them is trying to merge solid layer heating that's been classically studied along with fluid layer heating. That's sort of an emerging field. And we do this along with Robert Tyler, also up at Goddard Space Flight Center, who's an expert in fluid layer heating. And what these phase spaces are trying to say, this for solid layer heating as a function of layer thickness and material dissipation parameters, it effectively has one resonance band in it and is fairly simple, whereas fluid layer heating on the same axes has quite a range of resonances into which it breaks up, all of which are important and need to be considered. What you get when you merge the two is, first of all, you get unique surface patterns of heating. You also get unique global equilibria in terms of global temperature. And you also just get more heat overall, which if you are a Europa analog would be good news. Another topic, and this is what our graduate student Joe Renaud is really making great progress on, is improving our mechanical models of the silicate layers or the ice layers. And you can think of how this works as most classical tidal studies have used the simplest mechanical models, and folks are gradually incrementing upwards in complexity. The complexity basically reflects how many grain scale phenomena in a mineral you are considering. And the simple models basically have a single resonance point in frequency space, which is sort of a mathematically pure idealized situation, not very realistic. Whereas what people see in laboratories for almost all materials is a broad frequency response, more of a continuum. So we are working towards those models. Now, we're also asked to mention possible collaborations for the team. So this is one that Sean Domago-Goldman and I have been talking about. Since the project has been looking at scattering cases and orbital migration cases, an interesting problem came up. And the idea is if you have a planet with a large water layer, either ice or water to begin with, and you start to increase the heating on it, either by insolation or by tides, other folks have studied in some detail the possibility of creating false positives for biogenic oxygen. If you vaporize a large amount of the water and the hydrogen is lost and the oxygen is retained, there's the possibility of seeing oxygen false positives. Now, tidal heat can play an interesting role in this process in two particular ways. The first is tidal heating has the unique ability to inject heat directly underneath a developing high albedo cloud deck and get heat directly into a layer that you would potentially be vaporizing. Whereas the insulation you may actually end up reflecting a very large fraction of your insulation, even if you're migrating. The other thing that tidal heating may be able to do, which insulation cannot, is it can suddenly turn off one day. As tidal heating sort of is wont to do when either the ice layer has completely vaporized or melted, or the orbit has fully circularized. So why does that matter? Well, for a false positive for biogenic oxygen, if it's super hot still, you're not really going to mistake it for a habitable world. But if the planet has had an opportunity to cool off because the source of what generated the vaporization is now gone, you might actually mistake it for a habitable source, and this is just another possibility that would need to be considered. So again, this is thrown out as a possible collaboration. If anyone is interested in working with Sean and I on a possible paper on this topic, would love to have your help. We need all the help we can get. And just the very last slide here. Again, talking about issues of orbital scattering, another fun topic has come up over the last year, which is the question of if you have a sort of cool, brittle planet which gets scattered by passage near a Jupiter, and it's thrown into a high eccentricity orbit, this is actually the absolute most perfect conditions to do some really serious geophysical damage to that planet. So we did a little study to try to figure out, could you do something like spontaneously rip open a Valles Marineris class rift in such a planet in the equivalent of a geological instant? Well, unfortunately for science fiction fans, the answer is no. You absolutely cannot do that. The magnitude of the rifting is nowhere near the 200 kilometers of a Valles Marineris type situation. However, you do get severe tidal stresses suddenly upon the planet, and you can still do damage. But what you're more likely to get is something like this. You can get a hairline fracture in the planet. Not quite as cool as the previous slide, but still perhaps interesting. Anyway, that's everything, and I'll open it up to questions and get off the stage for our next speaker.
A question from online. This is from Kostas. He says, is there any chance to get data about exomoon masses and such in the foreseeable future?
Well, as not an observer, I do not know for sure what's being done with that. I understand there have been some tentative exomoon discoveries out there. Other people in the audience probably know far better than I what the current status of some of the early claimed exomoons may or may not be. certainly hopeful that they'll start rolling in soon. I know people have been trying very hard.
Just a comment about exomoons. I was glad to hear about this project you're doing with Sean, including the volatile evolution, because I've often wondered if it's possible that a long time ago Io might have looked like Europa. And it's an interesting question of to what extent can that volatile or devolatilization be driven by tidal heating, especially in an environment with an extreme magnetic, like Jovian type magnetic field. And so just be very interesting to look at what are the limits of stability of a Europa type world and what might drive it to look like an Io-like world if indeed that is what happened.
Right, that's certainly a possibility, and there were some papers, I think, back in the 70s that looked at exactly that possibility, that Io used to have a large ice layer and it migrated inwards. I believe some of the limits on how much ice Io could have previously had are actually set by a volatile migration into the Io plasma torus, and how fast it can leave the torus. In fact, some of the situations look at sort of the magnetohydrodynamics of the ions go into the plasma torus, but they don't leave the vicinity and they just come back to Io. And the dynamics of that is sort of, plasma physics beyond my pay grade. But it's interesting that that ends up driving the problem more so than just the heating of Io. But I think the limits are that Io could have had an ice layer to begin with, but they're like 10 to 20 kilometers thickness. But those are studies that kind of were closed doors in the 70s and I think really should be reinvestigated with modern tools.
I was just thinking, I was looking at your slide that showed also the tidal heating, hydrogen escape, and this potential oxygen signature that you were talking about. Hot Neptunes basically don't exist, is what Kepler is telling us in some of the other surveys. However, in this batch of 1284 new validations that was announced last week, there's actually a couple of planets that sit right in that regime, and they could be just kind of temporary or rapid interlopers. Maybe they migrated in and they're in the process of actually moving down in radius because of these processes that we're talking about. I don't know if that's going to shake out in the long run. It'd be interesting to really make sure that we firm up their star properties and therefore planet properties. But if they do persist, then those would be very interesting targets to test some of these ideas without
Absolutely.
characterization. So check them out. Find those two objects that are there. They're really interesting.
That sounds great. Yeah, and for that problem, to overwhelm the potential to get an oxygen false positive for a long duration, you kind of have to overwhelm the mantle's tendency to absorb the oxygen. So you have to saturate the mantle. So you need to start with a very large amount of ice or water to begin with. So we are talking in the models that Sean and I have discussed about starting with thousands of kilometers of ice, which is very much more like a mini Neptune. So that's great that there may be some candidates to put some constraints on this. Thank you.
Thank you. You may have gone kind of fast for me, but having just been at the LPSC meeting in March, there are very few objects in the solar system now that don't have crunchy surface, subsurface ocean, slushy layer. We heard over and over again about looking at Sirius. Now we're thinking on Pluto. Do your models allow for having different kinds of multi-layered bodies, if you will, when you're doing your tidal dissipation?
Yes, in particular, multi-layer effects are integral to all the modeling that we are doing. If you do homogeneous modeling, you tend to get, orders of magnitude wrong results, and that was kind of a surprise. Like the first two slides where I was saying, suddenly we discovered the exact opposite effect occurred. That is due to a multi-layer modeling where, when you melt one layer, the increased dissipation is actually due to what's happening with the layer right underneath it. And so, yes, for things like, modeling Pluto or Charon in the past, that's definitely, a very important effect, and one which we've discovered is also incredibly important for getting exoplanet dynamics, really nailed.
All right, thank you.
All right, thank you.